You all right?
I'm more than good. Welcome to the Hackaday podcast. My name's Mike Szczys. I'm editor-in-chief of Hackaday.
Hey, I'm Elliot Williams. I'm managing editor of Hackaday.
This is episode 124. Today we're talking about hard driving with graphene, fooled by lasers, etching with poison acid, and all the Linux commands. I loved listening to the podcast last week. I thought you and Dan did an excellent job, and it's nice to just consume it rather than, plan and record and everything.
Yeah, welcome back.
Thank you. I have no idea what that sound was. Well, so you have not told me what that sound is, but I have an idea what the sound was. And I tried to find exactly what it was, and I couldn't, but I'm going to make a guess. Do we want to play it one more time?
Yeah, let's play it right now.
Okay, so I think that is a pulsar.
Ah, good. Okay.
Am I close?
Kinda.
Okay, because I've just the audio quality and some of the aspects of it are like pulsars that I've definitely heard before, but you can hear there's like a
yeah,
and that's a little different, so I'm not quite sure what that is.
Dew is exactly what I was looking for. It's a whistler.
A whistler, so it is a star.
It's a terrestrial phenomenon. Whistlers are what you get out of the kind of echoes of faraway lightning strikes. Because there's some dispersion in the ionosphere, the higher frequencies get to you first from the lightning, and the lower frequencies get to you later. And so that's why it makes that pew noise.
Right.
But there's a bunch of other things going on in there. The generic term for this, I guess, is spherics, atmospheric noises, and there were some whistlers. The other ones that have the really cool names are tweaks.
Yeah, well, we need to write an article on this. This is fascinating.
Yeah, we should do an article, and I bet Dan would do it because you heard the show last week, right?
Yes.
Dan is one of our resident ham radio nerds, and I'll be damned if he didn't pick that up instantly. I had to bleep it out. He was so right.
Yeah, you did the DTMF tones. To bleep them out. I liked it.
Did you decode what I typed in the DTMF?
No. Is there's a puzzle in there?
There might be an Easter egg in that.
Oh, man. Did anybody put it on the show notes?
Nobody did.
All right. So if you're listening, go to last week's podcast show notes and type it in there.
You don't announce your Easter eggs, do you? Maybe you do.
Let's see. No comments from last week. All right. So if you know what the DTMF are, or you care to, ridicule us for any other reason, go to hackaday.com/podcast to the June 18th episode and let us know. But we need to draw from these answers. So what did we get?
So, we got 7 right answers to this one. There were a couple really close ones, including radio emissions from planet Jupiter. And that's kind of up your alley on this one, Mike. Fireworks, meteor showers, sounds from the game Paratroopers. I don't know the game, but could possibly be. And then 7 right answers, which were like VLF, which is very low frequency, whistler, a whistler, spherics and whistlers, radio frequency whistlers, spherics from lightning strikes, etc., etc. So good job to all the ham radio nerds out there. Well, I don't have a 7-sided die. So this one, I'm going to draw from my computer's entropy pool, and I'm going to do it directly using dev random. And I'm going to pull a number out, and I'm going to convert it to octal, which will give me a last digit that's 0 to 7. And if it's 0, I'm just going to throw it away and do it again. So drum roll, please, as I type hex dump -b -n 1 dev random. The last digit is 6. Who's number 6? Mikey. Congratulations, Mikey. Ionospheric whistler. Uh-oh. Mike.
What?
Do you see what Mikey sent us?
What did Mikey send us?
A link to a Hackaday article about spherics whistlers in the Dawn Chorus.
Oh, no.
Oh, yeah.
I mean, awesome. But
you're like, we should really write this up. And I'm like, it'd be a great Hackaday article. And
I totally remember this article. It's like a bolt of lightning when you see Joe Kim's art, which is the Apple headphone silhouette guy dancing in front of lightning.
Plugged into the earth.
Yeah, plugged into the earth.
That's marvelous.
Oh, Dan's going to be mad when he hears this and realizes I forgot about this great article he wrote.
Oh, that's why Dan knew what it was. Dan wrote the article on whistlers. Damn it.
All right, so we'll put the link to that in the show notes this week because you'll have to go and read the old article. I don't think we'll cover it again. Aw.
No. Go read it. Go read it.
I do want to say that I wish you had drawn the number 2 because I wanted to say Sky Pickle. As people when they write in get to say what names they want said on the air, and this person said Sky Pickle. So thank you for your right answer, Sky Pickle, but unfortunately it was Mikey who won the shirt. I'll be in touch with you soon, Mikey.
Hi, this is Elliot in post. Mikey, your email bounced, so if you still want that t-shirt, send us an email, editor@hackaday.com. Thanks.
Let's dive into those hacks this week. I think you're up first, Elliot.
Starting off this week, I've got a video from Huygens Optics. This is tiny Tesla valves etched in glass. And I'll start off by saying the Tesla valves are actually kind of a red herring. Not that he doesn't etch them in there, but that's not the point. If you've been following Huygens, I think. Man, I don't know Dutch. If you've been following Huygens Optics' YouTube channel, you know that he's been doing some awesome explainers on making fantastic lenses and other odd optics. In this case, he's eventually going to be working on lenses and diffraction gratings and things like that that are created by etching ultra small features into the glass itself instead of grinding it. And this is the video where he starts showing you his crazy micro etching procedure. And when we say tiny Tesla valves, these are like, 4 micrometers across, and a string of 6 of these valves in a row is 300 micrometers long. This is super duper tiny. And so how do you etch things in glass? The unfortunate answer is the old-fashioned way, which is using hydrofluoric acid. And because of that, the first half of this video is a discussion of the horrible dangers of using hydrofluoric acid, and in particular how he was mitigating them, which include a hood and ultra heavy-duty gloves. And because the problem with hydrofluoric, as he says, is not only is it an acid, but it's also a deadly poison. Poisonous enough that 2 grams of it will kill you. Oof. And everything basically is permeable to hydrofluoric. And so if you put it on your skin just absorbs it straight away. And you don't notice, but that part of your skin dies within a couple days. So the gloves are no joke here either. The stuff boils at room temperature, so you gotta keep it cold because the fumes are, of course, deadly poisonous. So hydrofluoric is no joke, but he's got it under a hood and he's got the gloves on. So, in the first 10 minutes of this video, he's got the safety taken care of, I think.
I will say that I was saving this for later in the podcast, so I'll say it again then. But I'm glad someone does stuff like this so that, safely and they know what they're doing, so I don't have to.
Yeah,
it's wonderful being able to watch this, but wow, that's some nasty stuff, Elliot.
Yeah, I am not a safety nanny, and I am not at all afraid of chemistry. I grew up doing, photography, and my dad's a biochemist, and I grew up with all sorts of creepy chemicals. I hesitate to say don't do this at home, kids, but this may really be one of the rare cases of actually don't do this at home unless you've built yourself a positive pressure hood and, have the adequate safety gear.
Well, I just enjoy learning more about the chemistry hacks because I have so little background in that. I think maybe 10th grade, I took an AP chemistry class, and that's the extent of my, formal chemistry training. And so the point that I don't even feel all that comfortable with the cupric chloride for etching circuit boards hanging around my house, And so I just enjoy, there's this, I think, is it Nerd Rage that does a bunch of, Nerd Rage does a bunch of just like seeing the processes, and that, just like electronics, like it looks so complicated from the outside, but when you break it down into its constituent processes, it's manageable. And the problem is like not knowing what you don't know going into it. Yeah. In this case, though, the results of the etch are so clean. It's really amazing.
Yeah, so let's talk about that next, because that's the second half, and that's the cool part by me, is that he's making these ultra small features in glass, and they're so small that you start caring about the under etching that you get. If you put a a mask on top of the thing you're etching away, the chemicals also eat underneath that mask, and it makes a little kind of, I don't know what, elephant foot shape underneath the mask area. And with something like hydrofluoric, almost everything you can think of as using a mask is also permeable to the hydrofluoric, so that's not going to work. It turns out that chromium isn't, so he does this weird two-step where he plates the glass with chromium, covers it with a photoresist, etches away the chromium in one place, cleans off the photoresist, and then throws the hydrofluoric on to etch the glass. He gets absolutely phenomenal results out of this, and it's a really interesting process. Along the way, he mentions the other way to do this that unfortunately ends up with about $300,000 worth of machinery to do it. And he wryly jokes that he's going to have to wait until September when his birthday is coming up to get the setup for this one. But that's laser-induced etching, where you use the laser to put enough power into the glass that it like melts the glass a little bit, and then that small melted portion can react with actually a less caustic chemical and get dissolved out. And that looks really awesome, but it requires a highly tuned, extraordinarily well-focused, short pulse, high energy laser. And that's where the hang-up is here. In comparison, this photoresist method is pretty easy. And I guess we have to get to the punchline here, which he does at the very end. He says, everybody's doing Tesla valves on YouTube. I'm going to make my tiniest Tesla valve here. And it must be certainly the tiniest Tesla valve in existence because it's so tiny that it doesn't work at all. Capillary action just sucks the water the wrong way up the valve. So it isn't a valve at all at that scale. You have to get to a macro scale where the capillary action is dominated by the like momentum of the fluid.
Well, he also put the valves, there's multiple valves, like 8 valves tracks on here.
Right.
And 4 of them are going one way and 4 of them are going the other way.
Yeah, so, but they all flow backwards.
Right. They all fill at the
instantly.
same time. Yeah. I think the point of this is you have these teardrop shapes, and it's the eddy currents that are induced when you force a liquid through in one direction that make it more and more difficult for liquid to keep moving. I think there's probably just not enough molecules involved.
This is not good for microfluidics, but that wasn't Huygens Optics' point here. Anyway, his point was that Tesla valves are good for YouTube points.
Well, this works really well because the next one is a project that is complete BS as well.
This wasn't BS at all, by the way. This was just fun show-offery. And, kudos to that.
But the one I have picked is a fake. It's a phony, but it makes me hope and dream, Elliot. And so I really want to talk about it. And so this is a project that showed off a laser diode in a cylinder with 4 wrapped coils of wire on the cardinal directions on the outside of the cylinder. And then supposedly you could drive alternating current through these coils and have it deflect the laser diode, the actual body of the diode itself, which is just hanging on some wires, fast enough that you could then draw on a projection screen with it. It's a great idea because this is exactly how CRTs work. And so if you had something on there that was magnetic, I think part of the problem is, what are those coils pushing against on the diode? But if you had like a ferrous housing, you should be able to push against it. But then the picture that's being drawn is just way too high definition. It's like way too good. And I think I even saw you in the comments, Elliot, talking about, I can never say this word, Lissajous? Is that how you say it?
Lissajous. I don't know. In English we say Lissajous. It's probably French and it's probably Lissajous.
Right. And those are the kind of loopy, spirally patterns that you can get if you kind of circuit bend a CRT tube. And I think that would be like, this is a good idea that somebody should try and build. You're not going to be able to get the results that are being shown here because they're fake. But like here you have a mass of something. And so it's going to be very difficult to get that mass to be guided quickly without overshooting and to make, to turn on a dime and stuff like that. But I bet you could do something.
Like you say, it's on the edge of possible. And that led a couple people to speculate that he had tried to do something, come up with this apparatus, and then it turned out not to work. So he just faked the results. And indeed, he wrote into the tip line and apologized, which I think, good on him. He wrote into the tip line and apologized. He said, indeed, he tried to make this project work. He couldn't. He faked the video for it and posted it. And while I'm bummed that that's the case with this one, I looked through his channel and he's done a bunch of other really neat things. So there's a flip dot project of his, Mike, that you'll actually really like. So you should check that video out. I'm now, of course, a little bit skeptical because I'm like, once burned, twice shy, right? I don't think it's implausible either.
Well, that's the problem. I think in this case, he should have just made the fake video and been like, this is what I was trying to do. This is what it was in my mind, is for it to look like this. And I went about building it and testing it out, and it's not at all workable. Like, it's just not going to happen. And I think that would have been, to me, also an interesting video, although maybe it doesn't have the viral hook, which is probably what you want if you're on that platform. But I mean, we say it all the time on here, like the fails are as interesting or more to me than a lot of the stuff that we look at, just because you learn so much from them. And those wacky ideas that you can't pull off might be ideas that someone else can.
If you look at a lot of the YouTube channels that we see, they start off with a failure and a failure and a failure, and then come to kind of a, I got this working. And sometimes they don't. And like, I can think of a bunch of Tom Stanton's videos where he's trying to get this pneumatic engine working, right? And he goes through tremendous engineering effort and comes up empty in the end. But you're just as happy to see him working through all the problems one after the other and trying to solve them. So, I don't think it's necessary to fake it. And so I'm a little sad to see that happen. But, I think that's actually an awesome statement about where we've kind of come with this maker, inventor, YouTube video thing, that people are able to show their mistakes. Next up is a Linux article, a collection of Linux tools on steroids. This is a list collected by Ibrahim Dev and put up on GitHub, so you can actually submit your favorite Linux tools to this list as well. These are kind of intended to be modern command line tools for Linux. And so if you, use ls to list the files in a directory, there's a newer version that does the same thing but gives you fancy colors, or does subdirectories in a nice tree format and trims them so you can see it on one screen. And I'm always a sucker for this sort of thing because I'm a command line junkie, but I'm not a command line dogmatist, and you'll hear that in a sec too. I think these basic Unix tools are great. I may be a Unix dogmatist. I think that these simple tools should pipe into each other, and the output of one should go into the input of the next, because their strength is in the combination of them all. And a lot of these tools do have that nature to them, but not all of them. In particular, the ones I loved, I actually tried them all out on this list, and FZF is awesome. It's a fuzzy finder. You basically pass it a list, and then it lets you search that list using a really nice fuzzy find search as you go algorithm. And so if you're looking for a file in a directory, it makes it really quick. You just go ls and then pipe FZF, and then you can start, searching in a sane way through these files.
Ooh, that is really useful.
If you have like 10 directories nested, all of a sudden that's super fantastic. Because it's a Unix-y pipey tool, you can then pipe anything into FZF and do fuzzy find on it. So if you typed a command a while ago, but you can't remember what it is, you do history pipe FZF, and you just start typing until you find it. That's beautiful. That one's just an absolute winner, and that's my pick of the litter out of this. I'm using that tool now. FD is good. broot is good if tree lets you down. But then there were a few others. Like there was this one that is called choose that's basically like a little bit syntactically better version of cut. And cut lets you split up a list of arguments by, say, white space and pick the second one. Choose does this too. You type choose 2 and it picks the second, well, actually the third because it's 0 indexed element out of this list you pass it. That's awesome, except to get this running on my computer, I had to download 500 megabytes of Rust compiler and other services to install this program that ends up being 2 megabytes. And if you look at cut, It's written in C. It's on your system already, actually, and it's like 37 kilobytes, no megabytes, and it does the same thing, just with a different syntax.
But now you can write and compile anything in Rust, Elliot.
That's true, and it's slightly unfair for me to say that, right? Because then I'm using these tools that are in Python, and because I have Python already installed. Yeah, touche, Mike. You are totally right.
I pull stuff out of the terminal and use Python all the time, so it would be nice if I had a few more of these tools at my fingertips.
Can't leave without mentioning my kind of two favorite modern command line tools that didn't make this list, and I'm going to submit him a pull request. One is called dmenu, which is kind of like an interactive chooser, except it pops up a little curses-like window to let you pipe things into it and then choose them. It's really nice. It's not fuzzy finding like FCF, but it does do matching. And the one that I could not live without is auto jump, which is also kind of a fuzzy find like thing, except it's for directories. And so if you want to change into a directory, you start typing that directory and it takes you there without you having to type in the full path.
Ooh.
But it auto-populates its database of the directories on your disk and weights them by the time you spend in them. So if you're always working in one directory, like I'll do all my Hackaday work in a directory called staging, all you have to do is type J, which is the alias for AutoJump, and it takes you straight to your most used directory. You hit J again, it takes you to your second most used directory. You type J and then the letter F, it takes you to the directory you've used the most that has an F in the name. 2-3 keystrokes, and you are in any directory you use frequently, anywhere on your file system. That is a huge win.
Oh, that would be so nice to jump to different repos that I've cloned because they're nested in like a million subdirectories. I love the ability to find these, clever hints in Linux because where do you go for that? I mean, one of my go-tos forever has been Al Williams' series called Linux Foo, where he's pulling out like one thing and like doing something that half the people that see it are like, that's totally the wrong way to do that. And the other half are like, that's the coolest thing, I'm going to use it. And just to get that kind of, visceral discussion going between a bunch of people who are, their daily driver is Linux is something that I've never encountered in real life. And I just, revel in it whenever we get the chance to participate.
I have learned so many things from Al's Linux Foo column. It is absurd.
In this modern age of breakers, you may not take too much time thinking about fuses, but when you think about huge transmission equipment, you might run into a 5,000 amp fuse. And if you are photonic induction, you think to yourself, I wonder if I could generate enough energy to blow that fuse. And so we have the video this week that takes not one, not two, but 10 capacitor banks in parallel to generate 200,000 amps to pump through this fuse and blow it. It is bonkers.
I haven't seen a photonic induction video and when I looked at this, I found out why. He's been on a hiatus. He used to be like blowing up everything with these giant capacitor banks and hasn't been doing that for 3 years because personal life stuff. And so this is kind of his return to blowing stuff up with electricity, and a return it is with a bang.
Yeah, and I get it. I mean, it's a lot of work to, figure out what you're going to do in this video and, tell the whole story and not miss anything along the way and then edit it all together at the end. But boy, am I thankful that he is because, and here it comes, Elliot, I'm really happy that someone is doing this really dangerous stuff and they know what they're doing and they do it safely so that I don't have to, but I get to experience it anyway.
True enough.
In this case, the fuse is giant. It is like a cookie tin with two beefy copper slabs coming out the sides, the lid and the bottom of the cookie tin. And he actually takes the sides of the cookie tin off. And in it, you can see there's all these strips. So there's actually like 50 100 amp slow burn fuse strips. Or maybe they're fast burn, I don't know. But, fuses, basically you have an engineered weakness in them so that if too much current is going through them, they basically burn themselves up and physically break the connection. So, the way fuses work is not very complicated. The way that you put this together to test this really high potential fuse is shocking. I couldn't help myself. He does a great job of, showing us, building bus bars out of, it looked like just copper bar. I don't know how big they were, maybe like 4 or 5 centimeters by 3 centimeters,
Right.
to get all these things together. And then there's a braided mesh material to jump. But when it comes to connecting the bank, he makes these huge cables that are highly insulated, and you need like a pneumatic clamp to, do the crimp connection on these. And I'm just looking at it, I'm like, this is wild. And then, I know so little about this high voltage stuff. It's like, how do you even know that all of the potential is gone? Like, how do you safely approach something like this after you've done the test run with it?
That's why you have a chicken stick, and he uses it a bunch, right? He's got essentially a jumper cable, and he'll hook one end of it onto the device, and then he'll take the other end on a long stick and connect that to the other side to completely discharge it. And if you watch him carefully, you'll notice he discharges it once, and then he discharges it again and maybe another time, because capacitors have a dielectric. The dielectric can still hold a little bit of residual charge, and it like comes back. It like has this weird spring back. And with a regular capacitor, that spring back is 0.5 volt. With one of these capacitor banks, that spring back is 20,000, 40,000 volts. So he's pretty careful about his stuff, although, he is famous for having burns on his rug.
He says that in this video. He's like, no burns on the rug because we're doing it outside.
Yeah, right.
One of the other really neat parts is just seeing the trigger that he makes for it. And in this case, there's one of those switches underneath a red protector for like arming the system. But when you actually want to fire it, it's a pneumatic switch. So there's a hose that goes, I don't know how far back, 10 meters back, and has kind of like a bladder that you step on that actuates through the air pressure, a switch in the box. And he says, when you're working with this much potential, you don't want to have any conductors around you that could potentially have the power come back to you.
We've kind of buried the lead here. This is a 5,000 amp fuse, but that means it's meant to carry 5,000 amps. And so to burn the thing out, you have to give it 30,000 amps continuous. And because that's just insane, he goes and gives it 200,000 amps over, a much shorter period of time. And there is no switch in this world that is rated to 200,000 amps and will open again without welding itself shut. So yeah, switches are consumable in this realm, and it's super important to be far, far away from the switch when you do the switching. I had a friend he had a huge capacitor bank, and we did some coin shrinking with copper coils. And of course there the coils explode. And so we all hid behind trees and we put cinder blocks all around it. And still there would be copper shrapnel everywhere, which is awesome. And so he was like not going to get zapped by this thing. And it was this like janky setup with 2 brass balls, and one of them swings to the other one and hits it, and a good half the time they would weld themselves together, and we'd have to come at it with a chisel and hit them apart to be able to use the switch again. Oh, good times. Coming up next, Caribou Labs has an interesting open source SDR. Raspberry Pi Hat adds SDR with high-speed memory access. You can check out this software-defined radio project on their GitHub. It's a really nice one. It does transmit, it does receive. It has a fairly high bit depth. That is, it's got 13 bits in both the I channel and the Q channel, if this means anything to you. You're an SDR nerd. It gets 4 megasamples per second. It covers the bandwidth from 30 megahertz to 6 gigahertz. It has an FPGA in it. It's a really sweet-looking SDR hat. And hat is where it gets really interesting. This thing fits on top of a Raspberry Pi and takes advantage of the Raspberry Pi's SMI, which is the secondary memory interface, which is meant to connect the system on chip on the Raspberry Pi to some other memory device. And that means it's a super high speed, super parallel interface. He's using that here to transmit this like flood of data coming in through this radio into the Raspberry Pi for processing. And that was actually the part of this project that I thought was super duper neat. And there's a great write-up of kind of everything we know about the SMI because it's not quite documented by Broadcom. In a link that I'll put in the show notes here from on the Lean 2 blog, which is Jeremy Bentham's blog. And it's a marvelous discussion of this SMI peripheral, which you can, through the Raspberry Pi's DMA ability, get a lot of data in and a lot of data out extraordinarily quickly.
Do you have to do any kernel stuff to get that running, or does it work out of the box with the OSs?
Jeremy has written a kernel driver for it. So
that's awesome.
You just have to use his software.
Yeah.
And the demo code for using it is just brutally simple. It's, it's like blinking LEDs. It's really, really easy. And the SMI peripheral has a DMA for it. So basically it wants to take in 32 bits and then it takes care of clocking them out for you. So if you have to clock out 8 bits at a time, it'll set one out and then it'll set the read line and then it'll set the next one out in the read line and the next one out in the read line. And all of this at the hardware level so that your Raspberry Pi, which is doing a bunch of thinking and multitasking, doesn't mess things up. There's a caveat here, which I thought was super interesting. This works better on the Pi Zero than it does on the much faster Pi 4. Why? Because the Pi Zero is a single core and the Pi 4 is a multi-core. And I think the Pi 4 is using the DMA bus somehow to communicate among its 4 different cores. Of course, nobody knows because this is all going on inside the Broadcom black box SoC. But it's empirically true that there's a lot more jitter on the faster Pi 4 than on the Pi Zero. And rounding this one up, I went back into the history of Hackaday and found an article of his where he talks about his hacking around with the SMI. And that is running way more LED strips on a Raspberry Pi with DMA. And that's from last year. You should absolutely go check that article out. It's, a 16-channel bus coming out of the Raspberry Pi using this SMI to drive like WS2812s or something, 16 channels of them in real time. It's a really awesome demo of what you could do and how easily you could do it with this secondary memory interface. I've talked so much about that. I think it's really cool. If you're interested in software-defined radio, check out this Caribou Labs offering. It's like one of the cooler software-defined radios I've seen in a while.
I had to pick this next project because it looks like someone that just had a bunch of extra parts around and decided to throw them all into the same project. But it's actually a consumer good. You can buy it and it works and it's great. It is a 19 coils make charging wireless. And this is a wireless charger by Xiaomi that you can buy to charge multiple items. So if you have 3 phones, you can line them up across this thing that is the size of a meatball sub. There are some wireless chargers that work better than others. I like wireless charging. I find that after a while of like plugging the same USB cord into a phone over and over again, the cord doesn't go in as well, and you have to dig out the lint that's in there from your pocket, and it's not a big deal. But if you don't ever have to plug anything into your phone, that's pretty cool. But I've one like kind of first generation or early generation charger that, boy, you have to have that thing exactly on there. And then I have another one that just, you can kind of put the phone anywhere on it and it charges great. And I always thought that did it with some kind of like phased array magic in there. But in this case, you have this meatball sub-sized thing with these 19 coils overlapped like the Olympic rings all over the top of it. And I think the way that these work is they have like a low power AC that they send through the coil, and then they measure what they get back, and that can tell them if they're coupled well with the receiving end of the charger. And so, I figure the way these are working is they're just constantly sending out that signal, and then when they get something like, oh, it's really strong right here, let's charge this thing right here, which makes a lot of sense. I scratch my head on it a little because I would think that the coils would interfere with each other a little bit. So maybe there's some logic on that. But the rest of this, you get a really good teardown. And so you get to learn about all kinds of different chips that I'd never heard of before, and I don't think are all that common. Like, for instance, it's a Chips Vision CV90365 that's handling the power delivery standard and the fast charging for this. And then the board is just littered with these Adamant 8060K45D3, which is a dual NMOS, so N-channel MOSFET chip that is actually doing the AC driving for the coils. I don't think I put the chip down. There's another N-channel MOSFET chip in there too that it's littered with, and I couldn't figure out what those are for. But I sure did enjoy looking at how the thing is actually put together and what goes into making it work, keeping it cool, and packaging it up.
There are so damn many coils in this thing. It looks like it's a joke. It looks like, what if we put 2 coils in it? And then someone else is like, ooh, what if we put 19 coils in it?
Yeah, there's about 60 comments on this article, and I didn't go through all of them, unfortunately, before this, because I'm wondering if someone's got... Yeah, there's a bunch of people talking about switch mode power supply efficiency, right. And I'm going to have to go through and review this. Sorry, folks, I didn't do that ahead of time, but, take a look. I think you'll be impressed by, there's a silicone heat lube in there to try and transfer the heat off of it. There's a kind of a 3-board stack up for the substrate, and it's just a lot of cool stuff going on. Very long and detailed write-up that comes on this from Charger Lab.
I like the comments from a bunch of the wireless charging haters in here. For instance, the Roger V points out that there's a lot of heat management in the device, and he kind of says it all about wireless charging, because if you're managing that heat, that's wasted energy. The other one is, dudes, the irony of wireless charging is that it requires a lot more wire. And in this case, it's like 19 times a lot more wire. My first quick hack this week is Doom comes to the NRF 5340, a hack by Audun. Didn't we see this last week? No, we didn't. This is a Doom hack inspired by that one on a different chip, this time the NRF 5340 from Nordic. The cool bit about this is that he's using a lot of the same memory saving tricks we saw in last week's IKEA trad-free lamp hack, but this time it's also got wireless on it, and so he's got a wireless remote control to play with. Next up, David Tucker putting the flex on flexures. I just love flexures. I think that 3D printing makes making them easy. And this one is a flexure mount for a pen or cutter knife to mount on a CNC machine. I'm totally going to make one of these. It's springy in the Z direction, but not in X, Y, or any of the rotational directions. The comments here include a link to a constant force 3D printed flexure mount, which is fantastic looking, and to a UCLA mechanical engineering course in designing flexures yourself. Next up, Peter with Rockabye Baby on the Mechatronic Crib Shaker. Some babies like to be rocked back and forth, and rockers are so last century. These days, we rock our babies with a whole bunch of aluminum profile, a stepper motor, and a ball screw. I'm not kidding you. This is the baby rocking machine with absolutely the least backlash possible. I'm surprised he didn't put his kid up on a Stewart platform and rotate him around. And finally, Moritz Receivers using heaters to display time. Moritz writes for us, but he's also a big fan of making thermochromic clocks. And this time he's making a small one using resistors as heaters, but he's given up on trying to make it go black, that is, cool off in between digits, and he's just superimposing the next digits over it. It makes this lovely fade out, and I actually really like the effect.
First up on my list of quick hacks, Human Google, Ruth Freitag, Isaac Asimov, and bibliographies. If you're having a rough day, this story is going to cheer you up. I just love it so much. It's commemorating Ruth Freitag, who passed away just a little while ago, and she was a reference librarian in addition to having a strong background in science and having been in the public service for a long time. But she worked with people that you've definitely heard of and whose works you're very big fans of. Isaac Asimov worked with her for writing novels, as did Carl Sagan and a slew of other people. And I kind of like it that her entire job was kind of just like to know a lot of stuff and to be able to pull it together with like tight references and, you know, things that help people do the research and gain the knowledge that they need. She was kind of like the font of that knowledge in a time before things were digitized and dial up on search engines. I also think it's interesting in the comments to hear someone wonder if we've kind of lost something by moving away from the quote human search engine to the digital ones. And I think we have. And I think that we should value the people that have, you know, this background in things that can be very handy if you can remember the clever and cool stuff that is also, you know, puts the science in science fiction. Next up, I have a compact M&M sorter goes anywhere. I am just a sucker for these candy sorters, and this one is particularly delightful. It goes on top of a smart water bottle. I would think of it more like a mason jar, so it threads right on there. Inside the mason jar, a little 3D printed bracket has made chambers that are pie-shaped, and a cylinder above this glass has everything that you need to pour in your M&Ms and have them sorted by color. It's done with a RGB LED that kind of zaps them with each color, and then a photodiode measures that. You have two motors that sort it. It's your typical sorter, but well worth a look. And finally, Steady Hand brings GBA Cart back from the grave. This is something that Taylor purchased from someone else who had tried to reflow the flash chip on it. It's a rare cartridge of a game called Golden Sun. Upon further inspection, a bunch of the traces were damaged, and I think further damaged in the second repair process. Taylor didn't give up. He actually used 30 gauge wire to reroute each of those traces. It's a wonderful example of how you can get yourself out of a bind with printed circuit boards. Now we're up to our can't miss articles of the week. This is long form content written by excellent Hackaday authors. What's on your list, Elliot?
This week, I picked one that's not super technical, but I just loved it. And that is Tom Nardi's teardown, France Crystal Metronome. And the backstory here is that somebody gave him this thing, said it doesn't work. Can you fix it? And this is something that I totally identify with. The number of, hey, hun, this is broken, make it work again, I get in my life are really ridiculous at this point. And that means I'm doing a teardown once a week. And Tom, of course, is the genius who's like, I'm going to photograph this thing and write it up for Hackaday. And I just love that because also this is an old metronome and it's got a speaker in it. It goes click, click, click. But it's in a really nice, solid walnut box that actually on the inside, when he's tearing it apart, is labeled solid walnut. There's a little sticker on it that says solid walnut, so you know it's hardcore. It's assembled together, it's nailed shut on the face, and, it's not much of a device. What does a metronome do? It goes click, click, click. And this one is a France Crystal metronome. So you'd look inside and you'd expect all the parts you see. You'd see some kind of old microcontroller, the dial, the speaker, some passives, and of course the crystal. And this is where Tom discovers the France Crystal metronome's deep, dark secret. The crystal inside is a ceramic resonator.
Oh, boo.
And he has a picture of it, and he writes in the caption underneath it, "You sit on a throne of lies." And I just love that. He also comments that France ceramic resonator metronome just doesn't have the same ring to it.
I thought it was interesting how difficult it was to tear this down, that you can't just get part of the board out. You physically have to take every piece apart. And it just makes me wonder about the manufacturing process for it. Looking at the picture at the top, do you have it up in front of you, Elliot?
Sure.
So that dome, that red dome light on there, I can just see that flashing. And I have a bone to pick with Tom on this, is I want to hear what it sounds like. And I went out looking for it, and I found a bunch of France Crystal metronomes, but they're not this exact one. But if you go to look at some of the others that have a diamond-shaped light on the top of them, they have the most satisfying woodblock click
talk
to them.
Talk.
Yeah, it's just wonderful. I use a Dr. Beat, which is the fancy 90s or early 2000s that'll do all kinds of subdivisions and stuff like that. And it's just not the same. Like these older devices, they do have this visceral thing that we've lost in the digital era. So I think Tom was right on it on that one. The other thing is I looked at the exploded view of this for a long time and I'm like, how are they going to keep all the spiders from getting in there and building their webs with that big hole in the bottom? Because it looks like there's just this rectangular opening beneath the 9-volt battery clip. But then Tom down in the comments, someone else said that. Tom's like, oh yeah, there's a battery door and I forgot to put it in that photo.
Which brings us to Tom's deep, dark secret in this one. He tears this whole thing apart just to have a good look at it. And what's wrong with it? The 9-volt battery contacts, which he could have cleaned from the outside, are the problem. So he fixes the battery contacts, gives it back to his friend. Everything works just fine. If it fails again, he'll look into replacing the electrolytic capacitors. But, switch out the battery contacts that were all rusty and cruddy, and it works again. So winner, winner.
I picked up Maya Posh's article this week, How Graphene May Enable the Next Generations of High-Density Hard Drives. I am known around the Hackaday bunker as a graphene fanatic, but the thing is, I'm always looking for, when are we actually going to use this stuff? It seems like it's been around for a decade at least. Yeah. And, how have our lives changed? But this actually could be it, and Maya does a fantastic job of diving into it. The spinning type of hard drive has metal platters inside of it that have a magnetic coating on them, and you change the polarity of bits in that coating in order to store and read back data. But in order to keep that coating safe, it needs to be coated in something. So it's currently coated in a carbon-based overcoat, which they abbreviate COC. Not only does it protect that magnetic material from corrosion, it also protects it from mechanical wear, because Maya says in this article, the heads contacting those platters is not all that uncommon, but if you have a good overcoat, it won't actually cause damage. Some of the drives these days even have a layer of lube on top of that in order to prevent any kind of mechanical wear that might be going on from them touching. And the problem that we get into is the COC, this coating for durability, is thick, I guess. I mean, relatively
on
thick.
On a nanometer scale, it's thick.
It's 2.5 to 3 nanometers thick. And if they can get the heads closer, they can get better granularity, which means denser hard drive. And in this case, a graphene layer could be used to replace this. A graphene layer would be less than 1 nanometer thick, so 2.5 to 3 times thinner than what we're currently using, and it would remove the need to use that lube layer, which doesn't play nicely with one of the newer techniques for storing data on drives called HAMR. It's the heat assisted magnetic recording. And so there's a research paper that did trials of this and did a control platter and a graphene platter and compared them to each other, and the performance was proven to be so much better.
Yeah, if you don't think hard drives have become fully magical juju, you haven't looked closely enough at them. These heads are floating nanometers above the platter and not hitting it all the time. And the thing's spinning so fast and. It's really astounding. Actually, we just ran an article, Mistaken Identity, Piezo Actuators, Not Test Pads, that points this out. And this is Dave Jones looking at the actuators on the end of the heads that go over the platters. And they're actually little piezo elements because they don't need to move more than, a couple microns in either direction. And so these are the motors that are wiggling the heads at the very end. Interesting stuff. But this whole heat activated bit flipping, because it's literally heating up parts of the drive, and then talk about the modifying the crystalline structure of the things that are in this surface so that they form little discrete crystals so that it's easier to magnetize a given region and not its next door regions. And then all of this is somehow abstracted away by some crazy analog electronics and then some error correction, and then finally it turns into bits that get into your computer. the chain from like magnets, how do they work, to bits being on and off seems plausible in a way, but it's so convoluted along the way and so full of like impossible technical hurdles that it's a miracle these things work at all.
Yeah, I already replied back to some guy on Twitter about this one that was like, "Oh, great, another overhyped graphene story." And I said, "No,
I hope
like,
so.
like
I hope
go
so.
and you hope it's overhyped or not?"
No, I hope we finally get one that works.
Oh yeah, we got to use graphene for something. Yeah, I guess maybe not everyone's as big of a graphene fan as I am. So graphene's so amazing because you can form a single atom thick lattice of this stuff. And I think it's a hexagon. Yeah, I think it's a hexagon shaped lattice. So it's really strong dimensionally in that direction, but it's also really thin. The problem is it's such a small, thin thing that like folding it, like if you were to try and make batteries out of this and you put it on some kind of substrate, plastic or paper, and then you tried to fold it, the folding can end up breaking the lattice. And, there's all kinds of difficulties with the manufacturing. So this has been proven that this could work, but it's proven in a laboratory setting. I think that it's well worth going and reading Maya's write-up on it because it uncovers and highlights a lot of the give and take of hard drive stuff and how this could actually work. And it's a good entry into actually reading the paper. But she comes to the conclusion that, the real gorilla in the room here is the manufacturing. Like, can you actually do this on one platter or can you do it on a million platters? That's a question that hasn't been answered. But in my mind, I look at like the ability to manufacture silicon wafers for chip manufacturing, and like we're really good at depositing very even layers of substances onto a flat disk in that particular case. I would think there's got to be some way to figure out how to mass produce platters that have this as the coating on it. It's not something that after you produce it is going to get moved or going to get exposed to a lot of wear and tear, or it's really just how do you get the stuff to the right thickness over this flat, very highly engineered surface? And that seems like it's a problem we can solve. That's all the time we have for this episode of the Hackaday podcast. As always, we'd love to hear from you. You can leave a comment on the show notes, which you'll find at hackaday.com/podcast. You can email us, editor@hackaday.com. We live and die by the tips that you send us, so if you've done something cool or you see something cool, please tell us about it. tips@hackaday.com. And until next time,
keep on hacking. Press record on this one.
The low-tech answer is the best.
Dude, I said too much. I'm going to say more too much. Heads up. My first quack kick.
That's an outtake right there.
Quack kick.
Clicking stop.
In time for the soccer game.